Good afternoon, all. People are still coming in, but I think we can make a start on today's seminar. So thank you all very much for joining. My name is Alex Shige. I'm a senior lecturer at the University of Auckland. It's my pleasure to introduce today's speaker, the NZSC seminar speaker, Professor Kazuhiko Kasai from Japan. So originally, the intention was that Professor Kasai would be in New Zealand for this presentation, but due to some last-minute changes, Professor Kasai had to delay his trip by 1 month, but still offered to do the presentation online for us anyway. So thank you very much. So Professor Kasai has had a very illustrious career. So he had graduated with his bachelor's in Japan, but then moved to Canada to do his master's in University of Waterloo, and then did his PhD in Berkeley, University of California. After that, he served at served in academic positions in various universities around the US, including Berkeley, Illinois Institute of Technology, as well as Lehigh University, before coming back to work as professor in Tokyo Institute of Technology, which has now been renamed Institute of Science Tokyo. Professor Kasai currently serves there as Professor Emeritus. So Professor Kasai is a very well recognized researcher internationally, particularly in areas of steel structures and response control. If I read this whole biography, it's going to be very long, but he served as a chairman for various committees on passive control and response control, as well as seismic isolation. He's led millions of dollars of grants in Japan, as well as jointly between the US and Japan, as well as having strong collaborations with research with Chinese colleagues. So Professor Kasai currently serves as the president for the House of Seismic Vibration Control Consortium, which has been addressing the seismic protection of 25 million houses in Japan. So with that, I'd like to pass on to Professor Kasai. Thank you again very much for joining us in your morning, Professor, and I'll pass it over to you to begin your presentation.
Thank you. Thank you very much, Alex. I really appreciate your very thorough introduction. I'm very glad to present some of my research here, and I would like to start now. I understand that time is limited, so we can talk later. The title is Japanese Building Retrofit Schemes Using Dampers for Various Seismically Defective Buildings. There are 4 sections. First one is various dampers supporting frames. After that, overview of just regular conventional retrofit scheme. Then I want to go over 4 retrofit examples using dampers. Then especially another one, I'm going to go for torsional damage collapse prevention by using dampers. I want to introduce my activity, especially for this vibration control. I was chairman for Response Control Committee and Possible Control Subcommittee for 23 years, and led the production of first to third editions of the JSSI Manual for Design and Construction of Passively Controlled Building. That's supposed to be very comprehensive, probably most comprehensive documents in the world, but it's written in Japanese. Since 2023, I turned over to chairman to 2 people, and I'm still working with them for the 4th edition. We just finished 4th edition, and 1st edition also vibration control manual for Japanese housing. This is something I'm focusing on. It's a new territory. In 2024, we published with 3 people: Professor Sakata, Matsuda, and Yamazaki. And in fact, yesterday I talked with the JSSI regarding how many buildings are vibration controlled, major buildings. He says 1745, but I talked with Professor Dr. Ian Aiken. I don't know if he's listening now or not. And he thinks that more than 2000, obviously. Yes, they may be missing, of course, they admit. So there are maybe 2000 or more major buildings with damper, and about 10% of them are retrofitted. And however, I want to note that the houses I mentioned here, there are almost 0.5 million houses vibration controlled, just because house makers are producing so many of them. And also there are many individual builders who make timber house on site, and there are dampers, some of them. But still, 0.5 million compared with 25 million houses in Japan. So there is also potential for further use. That's why we established the manual for the first time for the timber house and also light gauge steel house. Now, JSSI, coming back to JSSI, the fourth edition includes these: oil damper, viscous damper, viscoelastic, steel damper, friction damper, and inertial mass damper. Today, except this inertial mass damper, which is new, actually, I cover all these dampers. At least I mentioned them because some of the examples use those. Oil damper uses a very thin oil without much viscosity, no viscosity. This one uses very sticky oil, which has a very high viscosity. And viscoelastic damper is more like rubber and having stiffness and damping. Sometimes it shows ideal ellipse. Sometimes it shows a rectangular hysteresis at a bigger strain. We call nonlinear viscoelastic damper, which is becoming very common in Japan. And steel damper shows this hysteresis as familiar to you. And friction damper shows this kind of rectangular hysteresis. And inertial mass damper, because of inertial force created inside, the hysteresis becomes negative, have a negative stiffness on this one. Now, in addition to the dampers, we have various systems, which is very important. It's called directly connected system, wall type. It's connecting upper and lower beam. Therefore, story drifted directly into the damper. Very, very effective. And brace type also. The damper deforms most compared with others. And also shearing type. I want to show this and this too as examples. And also stud type. This is indirectly connected system. The reason is that top story and bottom story drift, and you have a force here, and then this causes a bending of the beam, and also column too, due to the damper force. Therefore, damper does not deform as much as these, not ideal. However, architect likes those because of the openings. Also, bracket type, I call knee brace. And this one also, sometimes they prefer, but it's not so effective because, again, this pushes column and column deforms it. This deforms less. Special system, toggle type, amplifier type are called. So these systems I'm going to cover today. But in those systems, very important, just like I say here, if there is a damper here and brace is here, if brace is soft, then brace deforms and damper does not deform, then it's not going to be effective. So like this one, if the damper deforms, but the other one, this is like a brace. So if brace, this deforms, it's not effective. So this is what you have to consider. And also KF. If KF is very, very stiff, like a concrete building, then these cannot take so much load. Most force goes to frame, then the damper is not effective. Therefore, damper and brace must be stiff enough. So in summary, the vibration control effectiveness depends on balance of three properties: brace stiffness, frame stiffness, and damper property or stiffness. So considering that one and ideal response spectrum, we develop performance curves. This is showing displacement reduction here and force reduction relative to 1. That means if you have no damper, the force and displacement are 1. And if you use a damper, for example, this Ka divided by Kf, there is a Kf only here. But if Ka, damper stiffness increased, the displacement decreased. And with also, for the case of steel, steel damper should show ductility. And ductility is larger, then it can keep acceleration smaller. And still, you can control displacement. However, if ductility is small, like this, 1, if the steel damper does not deform inelastically, elastic one, then obviously it can reduce the displacement. However, very big acceleration develops and the force is larger. So this one can give you the balance effect of the damper, brace, and the stiffness. The brace is here. The brace Ka over Kf. I'm sorry. This one is not here. It's a brace and the damper are considered to be total. But other one, you have to really separate between the brace and the damper because damper and the brace are completely different one. Damper is velocity dependent and brace is elastic and displacement dependent. So this one really talks about balance between brace and damper. The brace effect is included here inherently. Okay. Then, for example, we did E-defense test for the 5-story full-scale building. And let's see, 5-story building, I was a team leader for this one. And there are dampers here and here. And from 1st to 4th story, we had dampers. There are 2 dampers in this direction and 1 damper which is 2 times bigger in this direction. And we compared that one. I'm sorry, I think I'm skipping that. Okay, we compared that damper with, for example, here, our prediction with result from E-defense for damper yielding and developing ductility of 4, which we consider is best for the steel damper. And so it worked very well. We confirmed with other viscoelastic one, oil damper, and viscous damper. I'm going to skip those. The important thing is this performance curve can give you, for example, difference between free steel damper and friction damper. Both are considered to be bilinear dampers. If the displacement is reduced to be reduced to 0.45, then we have multiple solution, design solution. One is to use ductility 4, and with this stiffness, Ka over Kf equal 2. And another one is this. You have another solution here. Ka over Kf equal to between 2 and 3. So it's 2 and 4, so 3. And in this case, as you can see, the damper is stiffer and exhibits more ductility demand, mu equal 8. Steel damper cannot tolerate such a big ductility demand, but friction damper can. And so, but friction damper has to be stiffer. So this one is a very important aspect. As long as you can make a very stiff elastic stiffness, then required damper force here, this is a frame up to this drift. And so frame force is this one, but damper force is this one. This is friction damper force, and this is steel damper force. So you can see that the required damper force for the latter friction is only 50% of the steel damper. And so sometimes, of course, steel damper is very preferred very often, but friction damper has advantage like that. I'm going to show that example later. Now, now I guess overview of RC building retrofit methods in Japan. These are probably very similar to yours, so I'm going to skip very quickly. Firstly, number one is to reduce lateral load on frame, which is very important. Mass damper can do that. Another one, base isolation can do that. It can reduce the force on the frame. And also put the vibration control device, and they take the force. And as long as this is stiff enough, as I say, then the frame force, lateral force on the frame will decrease. So that's a reduced lateral load on frame. Another one is to avoid concentration force deformation into column. Even without damper, we have to be like that, right? You want to prevent shear failure of short column. And another one, overall, avoid concentration deformation into column due to building torsion. Christchurch earthquake, you had this CTA building collapse just because of torsion. Exterior columns got so much deformation demand. And another one, E-defense. I conducted other tests, just let it collapse. A soft story. The first column got concentration of deformation. Another one, pounding during Mexico City. I worked on pounding too. And this one is the case that the floors are different level. So some floor of one building really hits the middle height of the column of the other building. So you really have to avoid concentration for deformation into columns, whether dumped or not. This is very important. And the third one is strengthen frame members, each local strengthening. For example, you know familiar, column is too slender, then you can make it stronger. And steel sheet for beams, and also columns like this, and also carbon fiber, etc. Then finally, after members, you can say overall systems. For example, wall is not there, then you can put a new wall and or increase wall thickness by adding concrete here. And for example, this is very used for damper, adding steel frame. Steel frame takes damper force. And the steel frame is attached to concrete frame using stud and spiral reinforcement typically, or use adhesive material. These techniques are used for dampers. Now, strengthen overall system, the second one, you put the buttress or elevation and plan. For example, this one, balcony is too thin to translate damper force to the building, then you have to increase the thickness of the balcony and slab and elevation. Okay, you add this one. That's what I'm going to show. And number three, extension of structure outside brace structure, and adding extra braces, adding core, adding structures if you have some space. Okay, so much for fundamental ones. Let's talk about 4 retrofit schemes. Now, first one is a steel damper, buckling restraint brace. This is outside frame, and this has some space here between. So they try to use floor slab, balcony to connect this one. Just to utilize the balcony, yeah. And another one, I want to go very quickly on this one because it's the same with this friction regarding how to connect. Now, steel damper, buckling restraint brace, I assume that everybody knows about it, so I'm gonna skip it. But this friction damper, there are many types of friction dampers. And especially this Professor Kitajima, Nippon University, and he used to be an engineer of Asunaro Aoki construction. By the way, I have to give credit to Nippon Steel Engineering on this one, producing buckling restraint brace, and they gave me this presentation. And this one is from Kitajima, and this is a mechanism. When earthquake comes, this exterior or interior cylinders go and right and left. Then the copper is attached to the outer cylinder, and steel is attached to the inner cylinder. And there is a internal pressure created when they insert copper into the ring. And so it's a tapered, so that's very simple. So then you get a very big fastening force, and multiplied by 0.3 friction coefficient would give you damper friction force. And but this one, it cannot be so big, and it can be probably limited 300 or 400 kilonewton. So you have to use many, which sometimes is advantageous, sometimes disadvantageous, but okay, here is one. This case, friction damper here is 400 kilonewton, and the steel pipe is 190 millimeter diameter. And connection here, just because damper force is not so big, therefore connection can be very simple. You have 4 studs, 4 anchors, and pretension, post-tension bolt. That's good enough. And this is the process. This is a typically school building. You create the 4 holes here after rebar detection, and drilling and wrapping up surface and grout it, and then you attach this. That's all. Of course, at the bottom, you have to have anchor here. Now, very interesting pseudodynamics test was conducted on existing building, school building, 3-story, which has to be demolished. So what they did is they cut this here and here so that they can put 1 brace here. And assuming that there are many braces they can attach, but they want to see typical behavior of this building by pseudodynamics. They put the actuator here on this remaining building, so it can push and pull the roof of it. And this damper works very well. And we can measure the force of the damper by attaching strain gauges on the brace. But other force we cannot measure. However, if you apply top force only, shear force of every story is a constant, same. But the damper taking this one, so remaining part is frame force. And by doing pseudodynamics, about 1.5 times eccentric earthquake is used. And the damper retrofit test gave 32 millimeter roof displacement, and it's a shorter period like this. And another one, non-retrofit test, about more than twice this displacement. Therefore, after that, this is a reaction force. Of course, actuator also can measure the reaction force. So actuator force showed this much of a force, almost similar. However, deformation is very big for non-retrofit case. Then also, they measured damper force for the 2nd story, and taking out damper force and from the applied story shear, then they can get frame shear force. So when you have a damper here, you can reduce the seismic load on the frame like this. And therefore, the frame tends to be almost elastic, as compared to the non-retrofit case. After this test, they remove the damper and they conduct a non-retrofit test. And as again, I say that the force goes like this, and also deformation is more than twice. the force this and this, if you add, almost same. However, deformation can be very large compared with this one. And this also is evidenced by cracking. With damper, they could not see any severe damage. But after removing the damper and conducting a non-retrofit case, pseudodynamic test, then they got lots of cracking. Okay, so this is so much for friction damper case. And using brace type. And also steel damper case using brace type. Now, viscous damper with toggle system. You can see the very colorful toggle system. This is a damper, and this is a link, a brace, amplifying force. And damper can be smaller. Now, taking advantage of this, this is for school building. They painted in 3 colors, like a color pencil. It's good for elementary school, and they got the best design award in 2009. And people like this, very colorful. And also advantage of this toggle system is that each component is smaller. So they assemble that on site. They can transport relatively easily to the site. And the toggle system was used for Sendai City Hall. Sendai is often shaken by a strong earthquake. And so City Hall city officials decided to use toggle system. Somehow toggle system was put on randomly. I guess maybe there are some reason. And also there was some wall added. This is a typical view of the toggle system. And Kasai laboratory got some record of this building after retrofit, 2011 Tohoku earthquake record. And we processed so that to get damping ratio. Damping ratio is about 11% for the first mode, which is very nice. And so damper is working very well. And the frequency is 1 Hertz. Now, so that means we can use model out of this one. I'm going to show later. And this one is individual element is modeled and they made a share model. But then every story you have to make it. So this is 8 story, and therefore you have to stack 8 story. But this model is very detailed. For example, slackness occurs here. There is a pin joint. There are many pin joints. So you have to model the slip. And also you have to model the flexibility of the brace. They can deform. Therefore, if they deform or there is a slip going on, then the damper does not deform as much as you think, ideally. So very important to characterize those. And this is a result. And the result is, because of short of time, I'm going to very quickly. The conclusion is that the building behaved almost linearly. And this is a record versus analysis of shear model. Record is blue color, and it's a relative displacement of top floor, which was a double integrated result of the absolute acceleration. And also absolute acceleration of top floor. Analysis seems to work, but except this one, it's not very well here. Now, mode-based model, of course, works reasonably as long as structure behave roughly linearly. That's what I showed. Therefore, displacement of top floor and also absolute acceleration of top floor were very well predicted by mode-based method. And this one is very easy. So after Tohoku earthquake, our laboratory really processed many buildings by this one, because this one can take up only half a day to make a model. But this shear beam model takes maybe 1 week or more. But shear beam model is very advantageous because, for example, once you analyze with damper, you can also hypothetically analyze without damper. And of course, modeling is a concrete. And concrete, after a certain limit, for example, 150, it's really deteriorates. And therefore, concentration damage to a particular story level happens. And this is really why we need a retrofit reinforced concrete building. This is not reinforced concrete, steel building. 288 oil dampers are used by Taisei Corporation. And this is a view. Actually they use the short span beam and they put the damper inside. And also it's so close to the window, people can work in the daytime, and they did it only at night. And they didn't use weld at all. They fastened through the slab to the steel beam by post tension. And this is the way they conducted very effectively. And there was a record. So we processed by using modern method, like I said. And what we did is that we found that our modern method worked very well with the record. It collaborated very well. So after that, after we know, then the damping ratio was about 4% or so. So 3% or 4% only. But let's we assumed 1% in that model. That means we use the vibration period and mode shape, but we reduced model damping ratio from 3-point-something% to 1%, which is very typical for undamped case for the tall building, steel building. Then we can compare the difference. This is actually recorded with damper. And this is a hypothetical analysis that assuming no damper, therefore 1% damping ratio. You can see top floor displacement very, very different. And also another thing is that after certain cycles, you see that the one without damper still vibrates. So there are many, many cycles it has to go through. That frightens the people. Also, that can create some fatigue problem of the building on the non-structural component as well. So the damper effect is very well explained by this. Okay, finally, mitigation of torsional damage and collapse. I'm going to show two retrofit examples. CTB, Canterbury television building. This is also very important accident to us too, because we had 31 Japanese students studying English in this building, and they died. So then you can see that the core on the north side remained, as you know. So that is like I told in the beginning. It's a building with one side shear wall. And also there are many buildings, houses. You have to have an opening because of garage, they want to use it. So this side is very flexible, the other side is walled, so the building twists and collapse like this. Just like a torsional and also soft story column. So working about houses, as I mentioned in the beginning, we explored how to take care of this one by using knee brace type or bracket type, we called. And then we found that we have, as long as we do it carefully, we can have a very good effect. Firstly, we found very fundamental fact. The problem here is stiffness center. The center of stiffness is biased and compared with relative to mass. So therefore, the translation and the rotation of this part work in phase. And this is really causing lots of displacement here. Translation and rotation are in phase. Therefore, you have a very excessive column deformation, column story drift here, and very small here. However, if you put the center of damping opposite to the center of stiffness, and intentionally creating out of phase motion, it's a non-proportional damping case, then you can create no in-phase movement like this, out of phase movement, and that can minimize this rotation. And if you add this together, you will see that translation is very, very minimized in this side. And another one is just to see, after the theory, we found that, okay, simply at the target displacement, we want to make sure that this force or this force, even out of phase, maximum force can be same as long as we kind of target that way, regardless of out of phase. Then we found that it worked very well. Okay, then another one we have to also be careful is, like I say in the beginning, you have a damper here and you have a column. So the damper deforms, but apply the force to the column deforms. Therefore, damper cannot deform anymore. So, this one is stiffer, so damper can deform more. But this one, column is really strengthened, and then it can deform more. Therefore, the key point is really to have surrounding frame column very stiff. So that is just our preliminary study. And after that, we got practical opportunity. 13-story building retrofit using steel damper and stiff viscoelastic damper, reduction of torsional response, Kasai, Motoi, and Building Structure Institute. Those are the presenter is our student. Tokyo has been allocating $300 million a year to retrofit buildings that face emergency transportation roads, essential for post-quake recovery. During the 1995 Kobe earthquake, many buildings fell on such roads. And also, building at the corner, it can also interrupt two roads at the same time, which is very bad. So 13-story building built 50 years ago was decided, the owner decided to retrofit. This is a building. And here is a stiff part, and here is the open part. And fortunately, inside, there are beams here, and we can put the stud column, a stud damper, just like this. So we explore that one. There are 7 stud dampers in between the columns. And this is the one. The column, typically this size, and the beam is somewhat, however, long span. Therefore, as I say earlier, we have to be careful. This stud damper causes overturning on this beam, and beam with such a long span, even though you have a hunch, it's deforming and rotate. Therefore, it can reduce damper deformation and energy dissipation. So this is a disadvantage. However, it's a much better looking compared with a brace, and people liked it. And very typical, detailed finite element analysis was done in order to fasten to the existing beam. And this is a case of viscoelastic damper. Another one is for steel damper. And this is a testing of that damper with the stud. And this one is analysis is given by solid line, and that is using Kasai's viscoelastic model. Okay, so, and also overall analysis was done. It worked well, but not as good as this one. 5-story building retrofit using steel dampers, reduction of torsional response. There is a design office called Musa Laboratory, and I assisted there. And originally, stiffness center was here because they are stiff walled. And this is again, it's facing 2 streets. So there are lots of openings. This is just a simple facade with big window. So it's very flexible. So you go like this. And because mass center is here, so there is big eccentricity between stiffness center and mass center. However, after retrofit, by adding a stiffness here, we created here. It's like a facade. It's a, you may think it's a facade is very flexible. It's not strong. We create a very stiff facade, but without much thickness. That's what we did. And just like I showed, this one is a concentric case. There's no problem because you have a four. And this is a case opening, one opening. This is a case of our building. We call Tomon building. In just facing in front of very big station. So it's a landmark. And this is a case of that building I mentioned that. And Canterbury. And before retrofit, this was like that. There were boarding arrays on the fourth and fifth floor. So it was a big span structure. We didn't change that one. And just this two surface was too flexible laterally. And so we decided to put very stiff steel brace. And you don't need to put fireproof paint because outside they use the weathering steel. You can see the color of weathering steel. And also the force they take was directly going to very stiff arch they created so that people can still make access to the building. Here, it was cantilevered. So it was really torsionally defective because of inside column only taking force. This is a view of that steel truss. And here, the damper you cannot see is in here, but I want to show. Okay, here is damper, and still you cannot see. Okay, here it is. This is inside view. By the way, this building got award for the retrofit, best award in that year. And the design, architecture design was done by a very well-known architect who also designed pavilion for Expo in Osaka. Idea is this. Originally, all the building had aluminum facade, which is very flexible. But we utilize this beam and fasten the steel beam here by stud. So here is the damper here. And again, also the first floor, it was transforming seismic force from this slab to internal column, which is very weak. And this one now directly taking force by arch. This is the idea. This upper beam is connected to the upper floor, and lower beam is connected to the lower floor. But this one is very stiff. Therefore, when earthquake happened, this one is stiff but still deforms, but it is stiff enough to cause inelastic deformation of the link. We call link, or we call shear panel damper. Shear panel damper you are familiar with because New Zealand uses eccentric brace frame, and everybody can design it as if you follow the code, which is advantageous. Rather than buying ready-made damper, you can have this. And another advantage of this one is we can design freely. In this case, we made very, very narrow flanges. And that was possible because the reason is that here, there was a street, already street. So you cannot go over the street. Therefore, we had to create a very tiny workspace, about 1 meter. People work on this one. And we had to create very thin facade, which is strong enough with narrow flanges. And the unit was firstly transported to the site. Then after that, using the crane at night, not the working place, but this for the car, they use very tall crane, and they put the these units here. Then after that, they insert the unit through this tiny space, and people fasten that one to the floor beams. And so they conducted this way. Firstly, they created arch, very strong one. Then after that, they created this wall, facade, and then they go on further. Now, this is the result. Let's look at the roof displacement. Now, roof displacement, if you put x direction input after retrofit, I'm sorry, maybe third floor, after retrofit, you see it goes like this. But before retrofit, it goes like this. Just like I say, it's a two-way eccentric case. So x direction input can cause y direction movement too, and plus torsion. Therefore, very complicated. And this is a y direction input. Then, of course, after retrofit, it goes y direction only, not x. But before retrofit, because of the biaxial eccentricity, it goes like this. Plus, deformation is about twice compared with this one. And same thing with the roof. So overall, this three-dimensional analysis proves that our method of providing exterior very stiff facade and having many dampers. There are 56 dampers. Every story level, we had 14 of them. And the other side, you have a smaller facade, which there's only 6. So in total, 56 and 18, 74 small shear links are used, and successfully. Now, shear link, you know how to design. This is a report published by Kasai and Popov, and this is a proportion of the link. And you can have gamma A, which is allowable shear strain in terms of H over TW, which is this one, H and TW. For different aspect ratio, D over H, 1.5, 2, and 3, D over H. And so this is from Kasai and Popov's formula, which is now used by UBC or other American codes, AISC. And also, this we have to prevent not only that, cumulative plastic deformation and fatigue failure. And I conducted this one with my professor Popov, but the other ones were very well developed by Japanese. So we had 3 criteria to design the link used for that building. But that's all. I guess I covered, firstly, damper effectiveness, which is based on balance between damper, brace, or surrounding members, and the frame itself. For reinforced concrete, frame is so stiff, so dampers should have initially very stiff one. And therefore, friction damper tend to be very advantageous, because as you saw, the brace is very, very stiff. Steel damper, of course, buckling restraint brace has some stiffness. However, as you see inside, the core has smaller cross section. Therefore, elastic stiffness is not as big as friction damper. And then I talked about general RC retrofit schemes. They are probably same with New Zealand. And okay, 3 to 54 stories using different types of damper. Friction, steel, and oil damper, and viscoelastic damper. This one, oil damper also. And this one, torsional damage collapse. we use a 5 and 13 story. One is using viscoelastic damper, and 5 story is using steel damper, which can be designed by you. So we hope that the appearance is kind of unique. However, you can design very steep facade and put some damper here. The thing is, your target story drift for the concrete building is very small. Therefore, is as long as you have a small drift requirement, your requirement for the damper is not so much. Therefore, this kind of low-rise shearing can well take such a shear strain. So please consider this. And if you have some question, please let me know. Thank you.
Thank you very much,
Yeah.
Professor Kasai. That was a very nice presentation, and thank you for going through a lot of content within the hour. So very much appreciated. We've got a few minutes left for questions, and there's a few that's come through the chat, Professor. So let me just read a couple out to you. There is one here from Raja asking about how do you decide, what is the selection criteria you decide when trying to decide on a specific type of damper for a building?
Oh, what is
what is the selection criteria you use to pick a damper for a building?
Oh, it depends on many cases. Of course, economy is very, important for those people, and also the space. And it's really, how to select the damper. As long as you say that the frame system is the same, okay, let's select some damper for such a frame system. Then oh, this one probably is the best. For example, oil damper, it can work only for brace type, but it doesn't work as very well with the stud type, something like that. So there are many things you have to consider, but ultimately it is a cost and performance. Today, I talk about performance, depending on this configuration. Then you can look at the cost of each damper and also supporting frame. We are talking about retrofit. Which retrofit scheme is cheaper? And that is another thing. And especially for the final one, it is kind of very special, but it can be applied to many buildings. And this was very, very inexpensive because you didn't have to buy dampers and you didn't have to paint, something like that. Yeah, it's a maintenance free.
Yeah, so, I think
yeah,
in New Zealand, we also have a big problem with cost. We have a few buildings that need retrofit, but maybe don't have the amount of support that Tokyo has had for the retrofit of their buildings. I have one more question here.
We had to write 6 papers on this project. First 2 parts were done by a contractor and also designers. And they talk about how they can, optimize the economy of that one. Yeah, something like that. Okay.
There's another question here, shifting to the toggle type knee joint system you showed. I think this is with reference to that school building you showed with the pencils as the dampers. The question is, how do you restrain that free joint from moving out of plane?
Which damper you're talking about?
This is the knee joint damper.
This one? Knee brace?
No, the toggle system with at the school retrofit.
Yeah. Okay. The connection is very, very strong. So that it doesn't go out of plane. Yes, you are right. You have to worry about out of plane movement on that one, right? It really does not. If you look at let's see. Can you see? You cannot see.
We just see the first page of your presentation.
How about this one?
Yes.
Oh, okay. You're talking about toggle, right? This one. Yeah. So if you look at this one, toggle system, after this, right?
Yes.
Okay. Here.
This one. Yeah.
Can you see? So that it
Yes.
doesn't go out of plane. You know that? Very, very strong. Yeah. So of course, it can go a little bit out of plane, but doesn't go further. This is really they have to make sure. Yeah.
I have a question, Professor, and it's about.
One thing I forgot to say: if one component is under compression, the other component is in tension. You see, this is another reason.
Yes.
Yeah. Okay. Yeah. Go ahead.
Maybe I'll take the prerogative here to ask the last question, Professor, and that's if you have any advice or maybe techniques maybe implemented in Japan to try to minimize the cost of these retrofits. For example, I'll give you one example. In Taiwan, sometimes they ignore the foundations in their retrofits to minimize the cost. It's not perfect, but it still seemed to work in past earthquakes. So I wondered if Japan had any, I'm not sure if you should call them shortcuts, but techniques to try and minimize cost of some of these retrofits.
I don't exactly know. Yeah. I know some people still prefer conventional brace type, but like somebody asked today, it's a conventional brace type can buckle. So just like this configuration, but the brace is straight. It's not bent like this. So then some support like the this pink one can be another brace to support the brace, and that's a very cheap way of supporting it. So you probably have seen when you visit in Japan, and this is one thing they may consider for the economy. Yeah, but when you talk about really value of the building, and you want to also worry about the future earthquake. And in terms of long term, many people agree that this vibration control system is preferred. Yeah. As long as they can afford. But so today I mentioned that you can make lots of effort to make it cheaper. Yeah.
Okay. I think we're just on the hour here, Professor. I'd like to again thank you very much for joining us from Japan and giving us a very nice presentation. And thank everybody on the call for joining during your lunch break as well. So, Professor, I hope your travel plans work out and hopefully see you next month when you come over to New Zealand.
Right. I have already rescheduled. Yeah. So I let you know. Yeah. I really want to give another presentation if you are allowed.
Fantastic. Okay. Thank you all very much.
Thank you.